Hi, good morning. So I'm always hopeful that we have audio. So today is the 6th of May 2021 at approximately 8 a.m. every week at London time we do this webinar. Sorry, I'll just turn that volume down. We do this webinar for our ZP Developer Zone members. So let me go fairly quickly today. I do appreciate, as always, all the questions that came through on the forum over the last week, and I will try addressing those questions now. So every week we have this forum, and we have this webinar, and we have really a series of kind of questions and answers. But I also think that the members of the ZP Developer Zone equally have the answers as well. So it's not just ZP answering this. It was nice that some of the forum members are also answering questions from other forum members on the ZP Developer Zone. So I think we essentially appreciate that. So the ZP Developer Zone, we have these webinars, we have these collaborations, we have these jobs. Now I think it's worth saying that it's very nice that quite a few of the ZP Developer Zone members are actually quite keen to kind of come to the UK and maybe do a placement or an internship with us. So I think it's or collaboration with us, let's say. So it's probably worth knowing about. There's a couple of schemes that I'm aware of. So the Royal Society of Chemistry has a Analytical Chemistry Trust Fund. So I just want to kind of make you guys aware of that the Analytical Chemistry Trust Fund, they will give grants up to approximately £5,000 for somebody to come from certain parts of the world. Sort of Southeast Asia is quite well covered, to come to the UK and work with a company. So you can actually get up to £5,000 from the RSC via the Analytical Chemistry Trust Fund. Now at Zimmer & Peacock, we appreciate that spending something like 3 months in the UK with a budget of £5,000 is not enough. So as long as you're a Developer Zone member, and as long as we've kind of just chatted about it and agreed upon it, and we're also doing we're matching these funds as well, so that every sort of pound that the Analytical Trust Fund will give you, then ZP is also contributing £1 as well. So if you're interested in collaborating with ZP and you would like to kind of come and be on site with us for something like 3 months in the UK, then I would suggest that you take a look at this Analytical Chemistry Trust Fund. As I say, we're matching, as long as we agree with you and we have a chat online, then we're matching this. There's also something else that I became aware of this week called the Knowledge Transfer Partnerships. This is particularly useful if you're if you have a PhD in particular, and you're kind of interested to do a sort of postdoc in the UK, then this KTP is, we're hearing feedback that it's sort of like a 90% probability that you might get it. Now you have to drive it yourself, but ZP has to be involved, because for these KTPs you generally need a university academic, you need a company involved, and obviously you need yourself. So if you're interested in, because the ZP Developer Zone, I say it's all about collaboration. Well, of course, collaboration, there's you often need a fuel for that, and fuel is money. So there's a couple of funding sources available that ZP can sort of help you with, and I've put a link here. I'll also put this link at the end of this video, at the very end. So I just want to say that the ZP Developer Zone, we talk about collaboration. Of course, collaboration sometimes involves people physically coming to either ZP in Norway or ZP in the UK. And if it's ZP in the UK, here's a link that I'd like people to take a look at, and in that link you'll find some links to these two schemes, and take a look at it and then drop me a line. So every week we do this webinar, and the webinar is driven by questions that come from the forum. So we do appreciate the questions from the forum. So at the beginning of the week I take a look at the forum questions, and I try to start addressing those questions here. So there is a forum. You can only access it if you're a member of the ZP Developer Zone. I think many of you are, so I'm delighted with that. The questions that we've had this week were regarding multiplexing in Anapot, so I will talk about that in a second. Also about multiplexing in the quad pot, and I think that's, I'll address that in a second. Also, somebody wants some technical questions about our point of care board, or POC. So Zimmer and Peacock, we're an ISO 13485 company, so we're certified for the development and manufacture of biosensors and electrochemical IVDs, in vitro diagnostics. This falls into one category of point of care. So people use POC term quite a lot, point of care, and also RDT, rapid diagnostic testing. So we have a few boards on the website about that, so I'll answer some questions about that. I'm also going to discuss LMP 91000. So I would say over a decade ago, I was sort of researching glucose meters, and I realized, through careful reading and research, that a lot of the commercial glucose meters, and I'll just grab one just to kind of illustrate, everyone knows but just to illustrate what I mean. So a lot of the commercial glucose meters, for example, ones like this, actually contain a chip in them called the LMP 91000. So I realized, okay, that's interesting. So we do have some information up on the website about that, and I'll only say at this moment that that's from Texas Instruments, and if you Google LMP 91000, you're going to find an awful lot of information on our website. And then the other question is how to interface to our SBS Microtiter plate. So I will address that question as well. The first thing I want to do is, I found this quite confusing until I really kind of learned the true definition that, in potentiostats, when we're talking about potentiostats, then there's multiplexing versus parallel potentiostats. Now I know that the author of the questions, he clearly knows the difference between multiplexing versus parallel potentiostats. And I'm going to just give you a quick graphical illustration of the difference between them, which is just reminding me, I did see a very clever electronics engineer online the other day, and I've asked him to join the forum. So I'm deliberately trying to make sure that we have members of the forum who are also, whereas I'm an electrochemist and a chemist, I also wanted members of the forum who are also very strong in electronics. So I think I've identified a guy like that. He's based in Indonesia. So what I want to do is just quickly, it's clear to the author of the question, but a parallel potentiostat. So Zimmer and Peacock has a 12-channel parallel potentiostat, and that means that we can put 12 screen-printed electrodes. Obviously, these kind of little things. We can put 12 of these in parallel. We can pipette on top of them, and we can be testing all 12 at the same time. Now, the other version of sort of multi-channel potentiostat is multiplexing. And in multiplexing, essentially there's a switch that goes click, 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 click. But so you're only addressing one screen printed electrode at a time. So the instrument is essentially indexing through. Now that means that the instrument is lower cost, but if your assay is 2 minutes, on the parallel potentiostat you could have run 12 experiments in 2 minutes. In the multiplexing potentiostat, then that would have taken 12 times 2, which is 24 minutes, because it would have done one experiment, index, done another experiment, index, done another experiment, index. At ZP, we never use multiplexing potentiostats. We're nothing against them. The benefit of multiplexing, now we do sell them, but we don't use them. Now, the reason we don't use them is because time is really important to us. So if we can do 12 experiments in 2 minutes, because everything's truly in parallel, we would much rather do that than spend 24 minutes, because time is our most valuable asset. Now, not obviously, but multiplexing instruments are often lower cost than their parallel equivalent, because essentially with multiplexing you can have one potentiostat, that's one potentiostat and one switch. So you can talk to 12, for example, screen printed electrodes by just switching. But you've only got one instrument, whereas with a parallel potentiostat, you could actually have 12 instruments essentially all in the same box, so you get true parallelization. So at ZP, we very rarely use or never use multiplexing potentiostats, but we do use an awful lot of parallel potentiostats. And the simple reason is, if you're doing biosensor development, you need statistically significant numbers of tests and sensors to kind of make sense of your data, especially in the early days, where sometimes your reproducibility of sensor manufacturing is not great. So if you're trying to make a decision based on one sensor, it's really no good. 3 is not really that good. But of course, if you've got 12 tests at one concentration and 12 tests at another concentration and 12 tests at another concentration, then you can see that, statistically I see my signal versus concentration. So we do like parallel potentiostats at ZP. Now back to the specifics, really. So sorry about that. So on ZP's website, we have lots of potentiostats. We have a single channel potentiostat. This is probably the one that's most historically been commonly used by us and our collaborators. Now I am really a big fan now of the 12 channel potentiostat, because at this moment ZP has about 52 employees. If every one of our scientists could have a 12 channel, I'd be delighted. At the moment we've got 5 of these, but we're just going to get more and more of them, or we're going to build more and more of them, because they make the scientists in the lab just so much more efficient. So we are big fans of the true 12 channel potentiostat. We do have the multiplexing, and you can essentially see that the multiplexing, it offers a sort of lower cost, but with I'm not a big fan of it, because you can do 8 experiments, but if each experiment takes 1 minute, I could have done 12 experiments in 1 minute on one instrument, and it would have taken me 8 minutes on the multiplexing instrument. So not a big fan of it, to be honest. I'm quite a big fan of the Sense It Smart. I just put it in there because if budget is a real issue, then the Sense It Smart is the best option. The one I am a big fan of the EIS system. I can't overemphasize it now. If you're doing a binding type assay, antibody and antigen type assay, or antibody plus virus assay, or antibody plus bacteria assay, I'm really a big fan of the EIS. And I realize these days that the 4x here has confused some people. They think it's essentially a quad stat, but it's not. I'm sorry about the 4x there. This is a single channel instrument that does EIS, and it's really, really good if you are doing binding assays. We now do all our binding assays using EIS, because we've now invented Julie. It means our scientists can essentially go into the lab, they can gather EIS data, upload it to Julie, and start doing the analysis in Julie. So we have sort of developed a workflow, but I'm a big proponent of EIS. Now this instrument is not, I know the 4x indicates, and I can see why the questioner was confused, the 4x would suggest that this was a 4-channel instrument. Unfortunately, it's just a 1-channel instrument. So the instrument that we've historically used a lot in our business is the Anapot. It's a good instrument. I'm now a big fan of the 12-channel version of the Anapot, because I just love the saving on time. I'm not a big fan of the multiplexer. It's sort of, you might as well have well, it doesn't save you any time or much time. Sense Smart is good because it is the lowest cost instrument of this kind of quality that I've seen online, and I can't overemphasize it. If you're doing electrochemical binding assays, then I would definitely suggest that. And I know that there's at least 2 of those. For example, there's a large cohort of ZP Developer Zones members in Indonesia. There's at least 2 of these instruments in Indonesia. They're really, really good. The next slide is just some links, and I'm gonna after the webinar I'm gonna put. Yeah. So Ali's here. What makes EIS suitable method for binding assays? So I am going to answer this question. I appreciate the question, Ali. The reason being is this, that because what's happening is this: you've got this binding going on now, and you can look at that binding as a function of frequency, and you can then look at the capacitive effect or the imaginary effect, and the resistance and the real effect. So essentially, you've got multiple frequencies. So that means that if we're going to optimize this assay, we can optimize it in terms of the DC voltage, the AC voltage amplitude, and the frequency. So we actually have a lot of inputs to play with. And then we can look at the signal using the imaginary component or the real component. So that gives us a lot of parameters. And I'm a big proponent of this now, that we're actually using really good data science to say, okay, these are our inputs, and this is a way of looking at our signal. Which of these inputs gives us the strongest signal output versus concentration? So we're really, I'm not a proponent of, we do equivalent circuit modeling at ZP, we do. But I'm not a big proponent of it, because actually, if you're a biosensor developer, you shouldn't care about the equivalent circuit, you should just care about signal versus concentration. So Ali's question is, why do you like EIS? I like EIS because there's so many parameters we can play with on the way in of the excitation, and then actually we get at least 2 interesting ways of looking at the signal, the real and the imaginary component. And so we look at is the strongest signal in the real component, is the strongest signal in the imaginary component, or is it actually a function of both components? And so we're using data science and AI and machine learning. I sort of mix them all up together, but we are the biggest and the fastest growing group at ZP. Is it the engineers? No. Is it the scientists? No. It's actually the data sciences group. So I'm a big fan of EIS because it gives you so many levers and handles to pull upon. And we, whenever, all our programs now, we've just discovered EIS is giving us the most benefit. So these are just links that I'm going to put up under the video afterwards. I've said it already, but at ZP, we do put these on the website. This holder is essentially for holding 12 screen printed electrodes in parallel. And this was a picture taken this week in a hospital where we're doing some development. And for real, we are going into these places, and we're not trying to test one biosensor based on screen printed electrodes. We're testing 12 of them at a time. So yeah, you cannot do really good biosensor development unless you've got large numbers of data points in your paper or in your research, and that's why I'm a big fan of multi-channel 12-channel potentiostats. And these adapters are something that we put on the website as well. Now, the questionnaire, when I looked at this week's questions, it was one guy who asked a lot of questions. I could sort of clearly tell that he had an electronics background. So he started asking us about this kind of board, and also he touched upon a little bit on this type of board. Now, the left-hand board we describe it on our website as a point of care POC board. Now, he asked me for details on this, and the problem is look, this is a multifunctional board, and I'm just going to grab the prototype hardware. So I will just come down slightly. So the exciting thing about working and collaborating with Zimmer and Peacock is you get to work on projects like this. Now this is the prototype, and I know I've shown it before, but what this device is, this is a cartridge. This is a microfluidic cartridge with an electrochemical biosensor embedded in it. And that electrochemical biosensor clicks into this instrument here. And then this instrument so essentially what happens is this instrument is what I'm doing is I'm blowing into it, and the device will measure parameters around my breath in terms of breathing rate, breath humidity, but what it's doing is it has a Peltier in here, and it's actually going to condense my breath, and then it's going to fill a microfluidic chamber which contains an electrochemical sensor and measure, for example, the amount of virus in my breath. Because we were having a conversation about binding assays. So at Zimmer & Peacock we do binding assays, and we do them in unusual and very valuable assays. The reason I've said all this is we've got asked a question about, give me details about this point of care board. This point of care board is something that we use not so much in the ZP developer zone, but ZP is I think we're a pretty world-class contract developer and contract manufacturer of electrochemical biosensors, but we also do the entire instrumentation around these kind of sensors. And so that point of care board, the gentleman asked me for lots of details. Well, the details are on it. It's a multifunctional point of care board, which allows us to kind of have temperature sensors. It allows us to have humidity sensors. It allows us to drive a Peltier. It allows us to have memory on board. So we do that board because if somebody comes to us and says, I want you to contract develop me a electrochemical sensor for this, and I need an entire instrument, then we will use that board. And now next to it I've put another board. So at Zimmer & Peacock, the reason we can run the developer zone and offer so much service essentially for free is because we're profitable in doing this kind of contract development, contract manufacturing. Now the other board that's on the right hand side, it's a board that can measure 15 open circuit potential sensors at a time. So open circuit potential sensors is also another way of saying potentiometric sensors. And a form of potentiometric sensors is ion selective electrodes, ISEs, and the classic form of ISEs is the pH sensor. So I'm sort of giving you some high level details about both these boards. One of the boards is somebody comes to us and says, I want to develop a complete product, for example, collection and analysis of the breath, and therefore we can use that board. The other board is because we have programs where people want to measure not just one pH sensor at a time, but maybe 15 pH sensors at a time. And so we've developed boards for doing that. And I'll just give you a kind of, and as I say, we use it to develop things like this. I put this slide up a few weeks ago, where actually what I'd said was, we were starting to look at not one pH sensor in parallel, but actually 9 pH sensors in parallel. So I'll just go to the next slide. So this is a bit of a case study about how we used one of our boards. So we took one of our boards, which can measure something like 15 pH sensors at a time. We either connect it to 9 pH sensors, or we can connect it to a small pH sensor like this, where we actually have an array of 9 pH sensors in a very small array. And I'm very excited by this particular program, because what we've done is this: we've got this board and it can measure 15 pH sensors, up to 15 pH sensors in parallel. Now we're only using it to measure 9 at the moment, but we've built some nice software, or some good prototype software, so that we can actually look at what each one of these pH sensors is doing, we're making an electrical connection here to this board, and then we're saying, right, electrode 1 is pH 10, electrode 4 is also at pH 10. So we're actually able to get spatial resolution of what the pH is, but we're also able to get time resolution. So we're able to just keep on looking at these in true parallel way, able to look at all 9 working electrodes and see what pH they are and how that pH is changing with time. So I will just quickly, I mean, this is not the world's best video, but it does show you that we are doing this for real. This will be on YouTube, and I'll sort of do a link for it. But in this, the engineer just kind of screenshot her computer, and you can't see a lot, but she's going to, you can start seeing some of the pixels are changing color because she's essentially changing the pH. It's a really nice experiment, because what she's essentially doing here is she's dropped a bit of alkali pH on, and it's diffusing across this small array of pH sensors. So I think this is just, you know, intellectually very interesting, because, you know, we always think of pH as this kind of you know, fixed constant, let's say, but in many applications and many science, you know, pH has a gradient and it's changing with time. And so there's you know, a device like this allows you to kind of understand, you know, if you had a cell culture, you know, is the pH constant across my entire cell culture? Is it changing with time? So I just want to kind of give you an illustration of why we have that. I mean, if people are interested in things like this, I'd be super interested in exploring this with you guys. I've only got 3 minutes left. I appreciate people have got to go to meetings, so I'm going to try and be a little bit quicker now. We did have some questions about the LMP9-1000. So I want to say this, that at ZP, I no longer suggest that people build electrochemical sensor technologies on the LMP9-1000. I have to just quickly say, look, use the ADU CM355. I'll say it again, use the ADU CM355. It's a much more modern chipset, and it's much better supported by analog devices. So I'm going to put some links in the video down below. We have historically worked with the LMP9-1000, but we're now using the CM355, and I'll put some links. The last question is how we interfacing with something called our SBS plate. So I'm just going to answer this very quickly because I've only got a minute. We essentially use what's called a bed of nails. These are pogo pins that are pointing upwards, and the plate sits on the top of that. I was going to talk about Julie today, but it's 8:28. I'm sure you've got meetings, I've got meetings, so unfortunately I'm going to have to wrap it up. So in summary, there are opportunities to work with Zimmer and Peacock. We currently we have already received a Analytical Chemistry Trust Fund award, and a gentleman is coming to the UK and he's going to work with us for 3 months. And I would also recommend the KTN, that looks really interesting. Please, if you haven't signed up for Julie's, do sign up for Julie. I'll try and do more demos about it next week. And yeah, the live streaming is driven by the forum. So if you have any questions of ZP, then I'm happy to try and answer them every week in this webinar. And I'd also, you know, if you see questions on the forum that you know the answer to, yeah, please just, you know, jump in and answer them. It's definitely a conversation and not a monologue. All right, so thanks, Ali, for asking your questions this week. I appreciate you guys for coming, and yeah, we'll do it again next week. All right, so 8 AM London time next week. Thanks very much. Take care.